Assalamu alaikum, everyone. So we're going to begin with our first topic in the next semester, um, which is called as EDM or electronic distance measurement. So we have studied a few or many methods of finding out horizontal distance. So we started with pacing as the most basic method. Then we went on to measuring tapes. Then we measured horizontal distance using a tachyometer, which is basically an analytic lens in theodolite. So we studied different methods, but now we come to the most modern or most accurate method, which is electronic distance measurement. So we have a few other methods as well that we haven't done so far, or some methods that have become extinct. But some of these methods we will cover, for example, photogrammetry. So finding out distances by taking photographs, and then EDMs that we are doing in this lecture. Then we have satellite systems. So basically through remote sensing, we can do this. And then we have odometer readings, an old instrument which measure the revolutions, and then optical rangefinders and substance bars, something that has become extinct now. So we'll focus in this lecture on EDMs, which is electronic distance measurement. So how does this work? So EDM devices measure lengths by indirectly determining the number of full and partial waves of transmitted electromagnetic energy required in traveling between two ends of a line. So what we use in this method is an instrument that can transmit electromagnetic energy. And the wavelength of that electromagnetic energy depends on the atmosphere in which we're using it. Usually it comes with a fixed wavelength. But as we will study in other topics of remote sensing as well, that depending on what is the media in which the way that electromagnetic wave is supposed to travel. So based on that, we can change the wavelength. So in this topic, in this method, sorry, what we do is that let's see a picture from where you can understand. Yeah, so from this diagram, so let's say you have one instrument over here. So that would be our transmitter. And on the other side, you have a reflector. So what we are supposed to do is that we are supposed to find out the distance between these two. So on the first point, you set up your instrument, the EDM, and on the second point, you set up a reflector or a prism. Or for that matter, you can not, even if you want, you don't have to place anything. So this reflector prism is placed over here because you want to reflect back that electromagnetic energy. So the important thing is that there should be a transmitter, EDM instrument. Over here, a reflector, which can or cannot be there. You can work without it as well. So what happens is that you transmit that electromagnetic wave, and it has a specific wavelength. It travels, strikes onto that reflecting surface, and then it travels back. Now, essentially what we're doing is that we are transmitting a wave that has a constant speed. And what we are measuring is the time that it takes to travel from one end to the other, and then to travel back. And this is what we find. And then using these two, we can find out the distance. Now, remember that the distance that you get, if you take the total time, so that would be 2 times the distance. And in order to get distance one way, you need to divide it by 2. So this is the main concept, that you have electromagnetic energy, a wave of a specific wavelength, you transmit it, it strikes the other surface and reflects back, and the instrument measures the time the whole process took. The velocity is constant, and using the basic equation of distance, we can find out the distance between the two. So this is how the whole process works. Now, let's move back to the slides and see a few other details. So what is the significance of this method? So if you don't use this method, then most often what you use is a measuring tape. And as you have studied in your previous semester, that when you measure using a measuring tape, in order to make it accurate, you have to apply a lot of corrections. So we have sag correction, pull correction, slope correction. So all of those corrections you need to apply if you want to make that reading reliable. On the other hand, if you have this instrument over here, it can do that work in a lot lesser time and with much more accuracy. So that is why this instrument has gained a lot of importance. Um, some total stations have this instrument inbuilt as well. We have different versions of this instrument. We have the handheld EDMs, and then we have these tripod ones, which basically looks a lot similar to a theodolite. So, and then we have a number of modifications for this instrument. So with some modifications, you can measure both distances and angles. So it depends what model we are talking about, but the main principle remains the same. So, sorry, sorry. So the current EDM instruments use infrared light, laser light, or microwaves. The ones popular microwave systems use a receiver transmitter at both ends of the measured line, whereas the infrared and laser systems utilize a transmitter at one end and a reflecting prism at the other end. So that has to do with the different wavelengths. They have different behavior. Some wavelengths get absorbed, some don't. So now that we use infrared and laser EDMs, so they can reflect back, so you don't need a receiver. In the current generation, EDM instruments are combined with digital theodolites and microprocessors to produce total station instruments. So you will be using a total station in this semester. And usually a total station comes with an EDM, so it can perform all the functions inbuilt. And when equipped with data collectors, they can record field notes electronically for transmission to computers. And these are called as finish-to-finish systems. So basically what you did in your previous semester was that you manually noted down the readings, you drew a figure, and then you had to perform a number of calculations. So you did that during the entire semester in your labs. So that's pretty tedious. But now in these modern instruments, they come with data collectors. So you can input different coordinates and it can perform the calculations for you on its own. It can build maps, it can give you areas, it can give you volumes automatically. So a lot of benefits. So like we discussed, current EDM instruments use infrared light or laser light, and EDMs are classified as long range EDMs. They can measure distances from 10 to 20 kilometers. Then we have medium range EDMs that can calculate distances from 3 to 10 kilometers. And then we have the short range EDMs, which can measure distances from 0.5 to 3 kilometers. So you can see we have different ranges. And in order to cope with longer lengths, so you have those modifications instruments. So you have wavelength modifications so that it can travel for more distance without energy dissipating. So some laser EDM instruments measure relatively short distances from 100 to 2000 meters without a reflecting prism, reflecting the light directly off the feature. So this is something that we're talking about, that in order to use an EDM, you usually don't need a reflector. But as a distance keeps on increasing, then it's better that you use a reflector. Why? Because as the distance keeps on increasing, the strength of the wave keeps on decreasing. The energy keeps on dissipating. And if you use a reflector, it can concentrate that energy again. And basically, it can give you more reliable results. On the other hand, you can reflect the light of any surface, but since it absorbs some energy, so you don't get a very strong return signal. but it still works when the distance is not too much. But as you keep on increasing the distance, then it becomes a problem. So the microwave instruments were often used in hydrographic surveys. So that is basically when you perform these operations in water. So since water has different dynamics, not all electromagnetic waves can travel through water. So since microwaves travel better or gave better results, so they were used in the instruments which were used for hydrographic surveys. And also in poor weather, again, as the atmosphere changes, um, it can have different effects on how electromagnetic wave of a particular wavelength performs. So you have to keep those things in mind. So this figure shows a wave of a specific wavelength, and it has a specific speed, and the frequency uh, can be used in this equation. So the wavelength is equal to the velocity divided by the frequency. And this is something that we have already discussed. Now we come to the equation of how to find out distance using this whole procedure. So as I told you that what it does is it measures the time and the velocity is constant. So basically what it does is that it gives you twice the distance since it goes from one end to the other and then it reflects back. And the time that it's measuring is the total time, the time the wave left the instrument and the time it returned back. So during that time, the wave covered twice the distance. So in order to find out the actual distance, you need to divide it by 2. Therefore, you have 2 over here. And in the numerator, what you have is total distance in the form of wavelengths. Now, there is this concept of full wavelengths and the partial wavelengths. So what this instrument can do is that it can also measure the number of wavelengths. If you see in this figure over here, so this complete sine wave is a complete wavelength, right? But when it does the complete distance traveling, it can come back to this point, but the wavelength might not be complete, right? So in that case, this is called as a partial wavelength. So what it does is that it measures the total number of complete wavelengths. So you have one wavelength, two, three, and whatever the number gets. And when it returns back, so you can be a case where the wavelength is not complete. And this is called as a partial wavelength. So for this, what you have in the equation is the total number of complete wavelengths and the partial wavelength. And that constitutes a total distance because a wavelength has a distance associated to it in the terms of meters. So if you multiply it by the total number of wavelengths, you can calculate total distance and divide by 2 to get the length. So now we'll talk about how can you calculate that partial wavelength. So for that, we use this concept of phase shift or phase angle. So basically, the complete wavelength has a phase angle of 360 degrees. So that is this complete wavelength. So that means if it's 0 degrees at the beginning and 360 degrees at the end, so there is 180 degrees at the middle. And similarly, whatever the shape of the wavelength is when it returns back, the partial wavelength, depending on what is the extent of it, you can calculate the phase angle. So using that phase angle, we can calculate the ratio or the total partial fraction of the wavelength that has been traveled. So let's say if you have a phase angle of 135. Now, in order to say that Okay, the total wavelength is 360 degrees. So what fraction of the distance of the wavelength has been covered if the phase angle is 135 degrees? And this phase angle is measured by the instrument. So in order to do that, what we do is we divide 135 by 360, and whatever answer you get, that would be the partial wavelength or the fraction of the wavelength that has been traveled. And then what do? You add it back in the equation in which we had the total number of full wavelengths plus the partial wavelength divided by 2, and that is how you get the total length. So now the principles of EDM. So the velocity in vacuum is this much, and its speed is slowed somewhat in the atmosphere according to this equation. So V over C over N, the velocity in the atmosphere is equal to the velocity of the wave in vacuum divided by N. So this N is atmospheric index of refraction, and its value ranges from 1.0001 to 1.005, and it depends on temperature, it depends on pressure, so you can have different values at different times of the day. It depends on the topography. So basically it tells you about the atmospheric index of refraction. So more the value, that means the lesser would be the velocity, and that means more energy is dissipated. So this correction can be applied if you calculate this index of refraction, and you can apply it to your velocity, and some adjustments can be made in the calculations, and you can come up with the correct distance. So for short distances using light wave EDM, atmospheric corrections have a relatively small significance. But like we discussed, as the distance keeps on increasing, the errors keep on increasing, and that's when you need to apply corrections. And for the type of measurements normally encountered in construction and civil engineering fields, instrumental errors and centering errors hold much more significance than do atmosphere-related errors. So since in our construction, we don't have to measure very long distances, even when we're doing projects such as highways, we can divide it into small patches so the total doesn't get too much. So in that case, these corrections of atmosphere do not have much significance. What significance there is of if there is any instrumental error, or if there's some human error, or if you have performed the centering and leveling correctly. So those things have much wider uh, repercussions for your calculations. So here are some characteristics of the EDM, some basic facts that you can study. Prisms. So we discussed this earlier as well, that an EDM infrared or laser can reflect off a natural surface or an artificial surface, or you can use prisms. Basically, if you use prisms, so that means they are reflectors and they can concentrate the energy, and the return signal that you get is stronger. So there are lesser chances of error. So some EDM instruments can measure distances without using reflecting prisms. The measuring surface itself acts as a reflector, and EDM instruments can be used conventionally with the reflecting prisms for distances up to 4 kilometers. When used without the prisms, the range drops to 100 to 2000 meters. So like we discussed, that more the distance, the more there is a need that you need to use a reflector or a prism. And then again, depending on the equipment, light conditions, angle of reflection from the surface, so different factors that can basically make it compulsory for you to use a reflector. Targets with light colored and flat surfaces perpendicular to the measuring beam provide the best ranges and accuracies because of the different reflective capabilities of various surfaces. So if you want to get best results, the target surface should be light colored. And we all know why, because darker colors absorb energy and lighter colors reflect energy. And the objective over here is to get a stronger return signal. So that means you need more energy reflected. That is why light colored surfaces work best. whenever you're working with EM, electromagnetic energy, and flat surfaces perpendicular to the measuring beam. So if there's any curvature in the surface, that means more energy would be lost. So the ideal conditions are light colored, flat surfaces, and the surface should be perpendicular to the beam. So applications are expected for nearshore hydrographic surveying, inaccessible points in many areas of heavy construction. So this is very useful when the distance that you want to measure, the second point is inaccessible, or it is accessible, but it would take you a lot of time to reach there. For example, you need to cross a river. So in those cases, this becomes very beneficial, and you can basically measure a lot of different distances while standing at one point. And you can do this in isolation. So you don't need a partner. You can do this on your own. So there are a number of benefits of using EDM. So computing horizontal distances from slope lengths. So this is one problem that we encountered before in the case of tape measurements as well. So all EDM equipment measure the slope distance between two stations. If the EDM unit is incorporated into a total station instrument, then it can reduce these distances to their horizontal components automatically if you input the angle, but you can do the calculations on your own as well. So if the difference in the elevation is used to reduce slope distances to horizontal, and the height of the EDM instrument is known, the reflector is known, so you can basically perform the calculations. So let's see this figure. So we have these 2 points A and B, and what you're interested in is finding out this horizontal distance h between the 2 points. So this h is what we are interested in. But since it's a sloping ground, the distance that the EDM will measure for you would be along the slope. And what we need to do is we need to convert the sloping distance into horizontal distance. So for that, what we are going to use is that we're going to use the elevation difference between the 2 points and the sloping distance. And that basically forms a right angle triangle. And then by using Pythagoras theorem, we can find out the horizontal distance. So the instrument is already giving us the inclined distance. But what we need to find out is the elevation difference between the 2 points. So for that, if the benchmark of A is known and the height of instrument is known, and similarly at the other end, if the B point is also a benchmark, reduced level is known, and the height of the instrument is known. So using these two, we can find out the elevation difference, which is D. And then by using this equation, we can find out the horizontal distance. So this is how you can use an EDM to find out horizontal distance when actually the EDM is giving you inclined distances. So this is a very simple problem of the concept that we have just discussed. So a slope distance of 165.36 meters was measured from A to B. So this is a distance which the instrument is giving you. The elevations of the 2 points are given. Find the horizontal length of the line AB if the heights of the EDM instrument and reflector were this much. So what they have given you is the sloping distance, and they have given you the reduced levels and the height of the instruments. So using the reduced levels and height of the instrument, you can find out the elevation difference between the two instruments. And once you have that, you just plug in the equations, plug in the values into the equation to find out the horizontal distance from the sloping distance. So this is it for this topic. I'll see you in the next class, inshallah.